NASA is developing cutting-edge propulsion technology that could make the journey to Alpha Centauri possible in just 40 years. For now, interstellar travel remains a distant dream, hindered by the immense scale of the cosmos. But that may soon change. The upcoming Sunbeam propulsion system is designed to propel a research probe to an astonishing 10% of the speed of light, potentially unlocking access to star systems once thought unreachable. So how does this system work? What engineering breakthroughs are set to shrink the vastness of space? And could voyages to distant stars and exoplanets become a reality within our lifetimes? Stick around to discover the incredible concept NASA is counting on to launch humanity into the interstellar age. And as if that weren't exciting enough, the James Webb Space Telescope has made a stunning discovery. It has detected dimethyl sulfide in the atmosphere of exoplanet K2-18b, a molecule that, on Earth, is only produced by living organisms. This may be the most compelling evidence of extraterrestrial life we've discovered so far. Experts suggest that the vast oceans of this distant water world, K2-18b, could be brimming with alien organisms. Imagine sending a research probe to this planet, one capable of confirming the existence of these hidden life forms, maybe even capturing them on camera. After all, K2-18b is only 124 light-years away. In cosmic terms, that's practically next door. But when it comes to space travel, it's still an overwhelming challenge. Just 1 light-year spans an unimaginable 9.46 trillion kilometers. To put that into perspective, even after nearly 50 years in space, the 2 Voyager probes haven't traveled the distance of a single light day. And it's not because they're slow. They cruise along at about 61,500 kilometers per hour. But even at that speed, reaching exoplanets or alien star systems remains far out of reach. And that's an understatement, because K2-18b is far from the only celestial body believed to hold revolutionary secrets. In fact, astronomers have already identified several potentially habitable exoplanets right in our cosmic backyard. One of the most intriguing candidates is practically next door. Meet Proxima B. Discovered in August 2016, this exoplanet lies just 4.2 light-years away in the constellation Centaurus. It orbits Proxima Centauri, a red dwarf star that, along with Alpha Centauri A and B, forms a triple star system. As the closest known exoplanet to Earth, Proxima B is a prime candidate for becoming the focus of humanity's first interstellar mission. The challenge? With today's technology, sending a probe there would take between 70,000 and 80,000 years. But here's where things get exciting. Breakthrough propulsion concepts like NASA's Sunbeam system could one day slash that travel time dramatically, turning the distant dream of interstellar exploration into a reachable goal. Let's take a closer look at how the Sunbeam propulsion system is set to revolutionize space travel. When it comes to breaking speed records, nothing currently comes close to the Parker Solar Probe. NASA's high-speed Marvel recently hit a staggering 692,000 kilometers per hour, making it the fastest human-made object in history. Impressive, right? But how does that stack up against 100 million kilometers per hour? At first, that kind of velocity sounds like pure science fiction. But believe it or not, it's the ambitious target speed of NASA's new Sunbeam concept. That's about 30,000 kilometers per second, or roughly 10% the speed of light. At such a speed, reaching the Alpha Centauri system wouldn't take tens of thousands of years, it would take just 40. So, how is something like this even possible? Surprisingly, the core idea behind the Sunbeam drive is quite simple. Instead of launching with all the necessary fuel on board, the spacecraft would receive energy externally throughout its journey. Instead of carrying its own permanent power source, the spacecraft will rely on an external platform that delivers a continuous energy supply via a particle beam. And let's be clear, this isn't about sending a tiny probe to other stars and planets. The goal is to launch a full-scale, 1,000-kilogram research probe equipped with state-of-the-art scientific instruments. At the core of this cutting-edge propulsion system is a relativistic electron beam. In other words, we're talking about electrons accelerated to nearly the speed of light, generating enough thrust to propel the spacecraft across interstellar space. This beam will be generated by an external platform, specifically, a solar statite, positioned close to the Sun held in place by the balance of solar radiation pressure and magnetic forces. the statite will direct its high-energy electron beam toward the probe. By transferring momentum to the spacecraft, this beam provides continuous acceleration without the need for onboard fuel. The longer the beam remains focused on the probe, the faster it will travel. But wouldn't the electrons eventually scatter across the vastness of space? After all, they naturally repel one another. Fortunately, physics offers a solution: the pinch effect, an outcome influenced by Einstein's theory of time dilation. In simple terms, time dilation means that time appears to move more slowly for objects in motion when observed from a stationary frame of reference. A classic example is a moving clock that ticks more slowly from the perspective of someone standing still. When applied to the Sunbeam drive, this means that relativistic electrons, those moving close to the speed of light, are held together more tightly, as time dilation prevents them from drifting apart. As a result, the particle beam stays focused, even across unimaginable distances. What's the big advantage of this approach? If this bold concept ever becomes reality, it could open the door to interstellar travel within practical timeframes, allowing us to explore distant worlds and find out whether exoplanets truly deserve their reputation as possible havens for life. As previously mentioned, this also applies to Proxima B. While the planet likely has a tidally locked rotation, meaning one side always faces its star, creating a scorching day side and a frigid night side, it still lies within the habitable zone. This is the region around a star where conditions might allow liquid water to exist. In Proxima B's case, it's possible that a narrow twilight band exists between the hot and cold extremes, where milder temperatures could let water flow in liquid form. Yet, the truth is, we currently don't have enough data to know for sure. We can't say definitively whether such a zone exists, or whether life might already have taken hold there. An interstellar probe could help answer these compelling questions. Sunbeam is one concept under consideration, but it's not alone. Breakthrough Starshot, for instance, is tackling the dream of interstellar travel from a different, and much smaller, angle. Originally championed by visionaries like Stephen Hawking and Freeman Dyson, this concept revolves around a tiny probe, no larger than a microchip, outfitted with a light sail and propelled by an enormous laser array. Compared to this, a solar sail positioned close to the Sun seems far more cost-effective, not to mention the benefits a full-sized research probe would have over such a minuscule craft. But when will it become a reality? When can we expect the first Sunbeam probe to launch from Earth and journey to Alpha Centauri? The challenges ahead mean we'll need patience. Although Sunbeam looks straightforward and promising on paper, it relies on an entirely new propulsion technology that must be invented from the ground up. This includes not only the relativistic electron beam itself but also the critical need to maintain perfect alignment of the beam with the probe over vast interstellar distances. Even the smallest misalignment could cause the beam to miss the spacecraft, dooming the mission before it truly begins. Moreover, the beam demands increasingly more energy to stay effective as the distance grows. Since the solar station is planned to be positioned close to the Sun, we would need materials capable of withstanding the intense heat and radiation emitted by our star, the source of our warmth and life. Yet, here's the exciting part: many core elements of the innovative Sunbeam propulsion system are already in place. For example, the Large Hadron Collider at CERN can generate beams with energies exceeding those required for Sunbeam. Additionally, the beam guidance technology used in today's particle accelerators could provide the precise control needed in space. Reflecting on the Parker Solar Probe, we've already designed and sent probes that can safely approach the Sun. However, the thermoelectric generators that scientists hope to use to convert the immense solar heat into electricity currently remain theoretical. At present, no existing technology can turn these extraterrestrial solar power plants into a reality. The necessary advancements still need to be developed. Beyond financial considerations, this will require significant time. Consequently, even the most optimistic estimates suggest it will take at least 20 to 30 years before the first Sunbeam prototype is launched.